Those Space People, a podcast series of casual cosmic conversations with people working on exciting space projects. Welcome to Thermal Lens, a special series focusing on thermal remote sensing, created by me, your host Rachana Mamidi, Agnieszka Sojinska, and Jennifer Susan Adams. Agnieszka is currently a research associate at the University of Leicester in the UK and has been working in the area of thermal remote sensing since 2017. Jennifer is a postdoctoral researcher at the University of Zurich in Switzerland and is currently focusing on measuring land surface temperature over forests. Agnieszka and Jennifer are also chairpersons of the Thermal Remote Sensing Special Interest Group of EARCEL, the European Association of Remote Sensing Laboratories. This group aims to bring together all the relevant stakeholders and provides a communication platform in the form of workshops, special sessions, seminars, and more. In today's episode, Jennifer and I are joined by Dr. Claire Bulgin, Senior Research Scientist in Earth Observation at the University of Reading, and we're going to explore the complexities of land surface temperature data and the uncertainties that come with it. Claire will elaborate on the difference between error and uncertainty, where uncertainties come from, how space missions tackle them, and what data providers and users should keep in mind. If you are curious about the reliability of temperature data from space, stay tuned. This is a must listen. Welcome to the podcast, Claire. The very first episode of Thermal Lens, we had started with a very nice introduction to land surface temperature. And in later episodes as well, we touched about this and various aspects surrounding it, such as directionality and measurement techniques and so on. And I only learned recently from Claire that another critical topic surrounding LST is uncertainties. So before we deep dive into this topic, could you tell us what the term uncertainty means?
Hello everyone, yes I can indeed. So I think maybe it would help to start with explaining what the difference is between error and uncertainty. So those are terms that are often used interchangeably, but they don't mean the same thing. So perhaps I can explain with an example. Imagine that you had a handheld thermometer and you wanted to go outside into your garden and measure the temperature of the soil at the top of your flower bed. Now, we know that there is an actual temperature, a true temperature of that soil, and then we have what we're able to measure with that handheld thermometer. And it's possible that there are sources of error in the measurement that you make. So, for example, there might be a problem with the calibration of your thermometer, and it might always measure 1 degree warmer than it should do, and that would be a source of error. It might be that you've stuck your thermometer too deeply into the flower bed, and what you're actually measuring is the temperature a bit lower down than you intended to measure. That's another source of error. And it might be that when you try to read the temperature, the scale on the thermometer isn't very clear, and perhaps you can only read it to the nearest degree. So that's 3 possible sources of error, and that error is how wrong the measurement is compared to the true value. Now, the thing is that we generally don't know what the error on one given measurement is, and if we did, we'd simply correct for it, and we would give the true value. So instead, what we do is we give a measure of uncertainty. So we generate a kind of distribution of the possible errors that we can attribute to a given measurement, and the width of that distribution is what we call the uncertainty. And it's synonymous with the degree of doubt that there is in a measurement.
So now that you mentioned error, automatically what comes to my mind is obviously all these terms like accuracy, precision. And when dealing with, at least with satellite systems that I've dealt with, or satellite sensors, you always have this one word, bias. So how do all these play into uncertainties and errors? What's the difference basically between them?
Yeah, so all of these terms mean something slightly different. So the accuracy is really a qualitative term, which is describing how close what you're actually measuring is to that true value in general. So the precision is talking about the repeatability of the measurement. So if we take that example where I went into my garden and I measured the temperature of my flower bed, if I did that 3 times, how close would those measurements be to one another? And that's what the precision is. And the bias, which was the final one you asked about, that's talking about the systematic difference. So it's just one component of the error between the true value and what you're measuring. So in my example with the thermometer, that systematic difference is the problem with the calibration. So if it's always 1 degree too warm, then that is the bias, and that would apply to all measurements that you made with that particular thermometer.
And so perhaps before we go into too much detail about uncertainty and all of the different terms and how we calculate uncertainty, perhaps we can just touch briefly on why it's important for users to consider uncertainty, because it can get really complicated, as we'll probably hear about later. And so I think maybe, Claire, you could tell us very briefly about why actually users should actually focus on uncertainty and consider it.
Yeah, absolutely. So uncertainty is really important in terms of making decisions with data. So I can illustrate this with a different example. Imagine that you were looking at the diurnal temperature cycle in a particular location on a given day. So imagine that we had some measurements from satellite at an hourly interval. You can plot those measurements on a graph, and you can imagine that it'd be cooler in the evening, warming up during the day to a peak, and then the temperature would drop off again. Perhaps you had a scientific question that was saying, I want to understand what the maximum daily temperature is and what the minimum temperature is. So you can look at that graph, you can pick the maximum, you can pick the minimum, and you can say, okay, answered my question. But if you do that, what you're assuming is that the data are 100% correct and that there is no uncertainty in those measurements. Now, a lot of satellite products will come with uncertainty estimates. And if you took them into account as well, you might find that there's a large uncertainty on that warmest value, and perhaps, therefore, there's a large degree of doubt as to how warm the temperature actually was, what the maximum was on that particular day. And likewise, you might find something similar with the minimum. So what the uncertainty is doing is enabling you to see how confident you are in the conclusions that you've drawn from that data. And I think this is a trivial example in some senses, just looking at the diurnal temperature cycle over one day. But if we think about the context in which we are often using surface temperature measurements, we're looking at long-term changes. We're thinking about how the climate is changing. And then if we're thinking about using those data in climate services, governments are looking at those data, thinking, okay, what do we want to do in terms of maybe mitigation or adaptation type interventions? Then they really need to understand how confident we are in what we're seeing in the trends in the data to make good and informed decisions.
Yeah, I think it's really important, depending on what the tolerance is of the application in mind, and deciding whether or not the surface temperature data is actually fit for purpose. So perhaps we can now go into a bit of the nitty-gritty of uncertainties. So we've learnt about all of the terms of uncertainty, error, and precision and bias. And we now have this term called an uncertainty budget, which is something that most satellite providers give with their data, or they're planning to give with it. So perhaps you could tell us what an uncertainty budget is, why it's important to calculate, and how you would go about calculating it.
Okay, yes, of course. I think I might start with the final question, because we can use an illustration from earlier to explain this. If you go back to that example of the thermometer outside, and I mentioned 3 possible sources of error, so the degree to which you can accurately read the scale, the depth that you push the thermometer into the soil, and any kind of systematic calibration issue with the thermometer, they are 3 possible sources of error associated with that measurement. And this is the information that you need to start to construct an uncertainty budget. So the idea is that with any measurement that you make, you write down essentially what the measurement is, think about all the terms or the things that are used in that, and try to work out where all the possible sources of error are that come into that measurement. And once you've got each of those sources of error, then you can start to construct the uncertainty on each of those possible error sources. And so this is how you're going to start to build up an uncertainty budget. Now, when we produce land surface temperature from satellite data, we don't provide users with an uncertainty on each of those individual effects, because that would produce really large products and it probably wouldn't be that helpful. So what we do is you can add all of those together. So we provide a total uncertainty, and then we provide a breakdown of some of the components. And what we do is we group them together according to the correlation length scale of those uncertainties. So some of the uncertainties, if you can imagine the noise on the instrument sensor, there is no correlation between what that noise is in one observation and in a neighbouring observation. There are other sources of uncertainty. So you imagine that with a satellite sensor, you're doing a retrieval that's going through the atmosphere. So you may have some uncertainties that are correlated over the scale at which the atmosphere stays approximately the same. And so they have a different correlation length scale. And so we group the uncertainties from each error effect according to these correlation length scales, and we provide those components in the uncertainty budget. And the reason that we do that is because if we want to propagate those uncertainties into new products, then you need to do something slightly different with them depending on what the correlation length scale is. So we're trying to maximize what users can do with the information. And if we didn't provide the breakdown, they couldn't do the propagation in the same way.
And now perhaps we can take it back to a very specific source of uncertainty or source of error. And let's say, given your flower bud example, it would be that you put your thermometer too far into the ground and you were measuring a different quantity. So how would you actually calculate the uncertainty of this specific error?
Well, that's a very good question with reference to a better sensor. So if you have a sensor where you can more accurately assess what the temperature is of that top layer of the soil, you could then compare what you're measuring with your thermometer at a different depth and see how much that disagrees with the more accurate measure. Alternatively, you could try and do maybe a profile through the soil and work out what the temperature difference is and how much it matters if you've pushed that thermometer in a little bit too deep. And then perhaps you can work out on average how much people are likely to do that, because there'll be some resistance in the soil, so you're not going to go super deep. So with all of that information, you might be able to get a handle on what the typical range of errors might be on that type of measurement. And from that distribution, you can take the width to give the uncertainty.
So I understand, I guess, bits of it. Of course, not being from a thermal imaging, thermal remote sensing background, unfortunately, I only grasp like bits of it. So could you perhaps, for my benefit, take us through the life cycle of uncertainty? So at what point, if I really think about it, so there's this thermal image that's coming from the satellite. So we commission the satellite, it takes a thermal image, we get the image, and then there's this low-level processing, the basic processing of the image. And then at what point is this uncertainty quantified, and how is this? And also you previously mentioned it's propagated. So what exactly and how exactly is it propagated, and at what point does it end up with the end users? So basically the life cycle of it.
Yeah, absolutely. So uncertainties come in right from the very start. So with satellite data, we tend to think about product levels. So the first level one is what you're actually getting from the instrument. So this is like the raw observations from the instrument. And there are uncertainties already in those data. So you might have noise in the different channels for the sensor. You might have an issue with the calibration, for example, which is causing a bias. And so ideally, what you want to be doing is characterizing those uncertainties right at the very start before you even think about doing a retrieval of land surface temperature in our example. And then the next stage would be to do that retrieval. This is what we would call a level 2 product. So we would retrieve the land surface temperature. Now you've got two things that you need to think about at this point. You've got the uncertainties that came from the level 1, and they need to be propagated into the level 2 product. And then you've got new uncertainties that arise because you're doing a new process. So you're retrieving the land surface temperature. Mm-hmm. So this is where propagation comes in and thinking about new uncertainty sources. So in the land surface temperature retrieval, for example, you have, if we take there are different algorithms, as your listeners already heard about, in terms of how we retrieve the land surface temperature. But if we picked one where we used a coefficient-based retrieval, those coefficients have a dependency on things like what the atmosphere is doing, what the viewing angle of the satellite is. And so that's another source of uncertainty that we're introducing. So we propagate from the instrument uncertainties, we add the bit that's happening because we've done the retrieval, and that's our level 2. Now, typically, users don't want the level 2 data because the level 2 data is on the grid that the satellite imager sees as it passes over, and it's a bit difficult to use. And what they typically want is something that's on a regular lat long grid, because that's much easier to use. And so that transformation from level 2 to level 3, which is what the user typically gets, is that last transformation. And with that, you also need to think about uncertainties that might come in there. So, for example, if you were averaging a number of measurements in a grid cell, when we retrieve land surface temperature, we can't do it where there's cloud because we can't see the surface. So we may end up with fewer measurements than the total, so we're not covering the full area. And so there's a sampling uncertainty that we would add in at that point. Is that clear?
Yeah, that explains a lot of things. And then you mentioned instrument uncertainties and a couple of other sources of these uncertainties. So what are the different sources of uncertainties?
Yeah, so as I mentioned, at the instrument level, you've got things like calibration and the noise on the sensor. At the level that you do the land surface temperature retrieval, you've got the propagated components that come from the sensor. Then you've got things like geolocation, so making sure that the instrument is looking exactly where you think it's looking. You've got the uncertainty that comes from clouds. So we have to determine if there's a cloud present, and if there is, we want to throw away that data because we're not looking at the surface. But if we get it wrong, there could be a large uncertainty in the presence of a cloud. But if we get it right, there's no uncertainty related to cloud because there's no cloud there. There's also uncertainties that come because we use a rate of transfer model to know something about the atmosphere through which we're doing the retrieval. So that's another source of uncertainty at the level 2. And then when you move to the gridded observations, the main source of uncertainty is in the sampling, which I mentioned previously.
So I think it sounds actually really complicated. And when you think of a satellite mission and think of all of the calibration and the effort that needs to go into just developing the sensor itself and characterizing uncertainty, but then also going through to level 1, level 2, level 3. So this is quite a lot of information for users. And I was wondering, how are current missions actually dealing with uncertainties? How are they communicating them to users? So you've touched a little bit on this with the level 3 land surface temperature gridded uncertainty information. But currently, how are missions actually providing this information?
Yeah, so I think there's possibly two kind of strands to the answer here. You have the mission itself, so the people that send the satellite into orbit, and they are responsible for doing the pre-flight testing, and they hopefully make those data available, because the people that process the data and produce the products like we do, the land surface temperature, are not always the same people. So there needs to be a flow of information that comes between the people that are doing those observations and the people that are creating the product. So that's the first thing to say. And then you asked in terms of how we communicate with users. And as I guess I've illustrated, although I've tried to keep it not too technical or mathematical, it still is very complicated. So there's been quite a learning curve, shall we say, in interacting with users and working out how we can best communicate this information to users. And historically, I guess, users have quite liked to have kind of quality levels with the data, and then they can threshold those quality levels and they can say, okay, we're definitely using good data now. And uncertainty doesn't work in quite the same way. So within the project that I'm involved in, we have a climate research group, and they quite often get together. These are users of our data that are doing kind of case studies within the project, but also more widely than that. And they talk about uncertainties and they talk about what uncertainty means. And I go to conferences and I talk about it as well conceptually. And I think that's the first step in getting users on board, so they really understand what it is that we are trying to communicate. And then how they use that really depends on what they want to do with the data. So in some cases, they may just be using the data as they are, and then they can use just a total uncertainty, and they don't have to worry about any of this propagation kind of problem. It may be, though, that they want to, so one thing that users often do is coarsen the data further. So if we produce relatively high resolution, maybe 1 kilometre to 5 kilometre products, people want to know what's happening over my city, what's happening over my country or my region. And so they immediately want to take an average of the temperatures over that domain. And then they do need to understand the propagation of uncertainty. And so I think as a project, we're really trying to help with that. I've done some work with climate modelers, helping them to understand how they do that in their process and in their context. So I think that's the way in which we can help to communicate with users and get them on board with using uncertainty information.
In what way do you communicate the uncertainty information? So, for example, if we are talking about error, we talk about error margins. We say it's a 5% tolerance, for instance, when we are talking about in engineering terms. But how do you quantify and how do you communicate uncertainties with users? Is it at the pixel level? Is it at an image level? Or, in what way?
Yeah, so we produce products that have an uncertainty at the pixel level. So each observation has its own uncertainty. And it's fair to say that uncertainties are not, historically, you'd have one uncertainty or one error. Going back, the term was used wrongly, error measurement, for a whole data set. And we've realised in recent years in processing satellite data that the uncertainty is not the same for each observation. So we provide per observation uncertainties, we provide the total, and then we provide this breakdown by the correlation length scale. So in the example of land surface temperature, you have an uncorrelated component, you have a component that's correlated with the surface, you have a component that's correlated over atmospheric scales, and then you have a large scale systematic component.
And I think given that you provide all of these different types of uncertainties, the uncorrelated, the correlated, those related to atmospheric effects, I was wondering if there is something that the uncertainty can actually tell you about your data that you can't see in the data itself. So is there something that it can reveal related to climate studies or agriculture or any other applications related to LST that uncertainty has actually helped you reveal more than the data itself?
Yeah, I think there's a slight link in that question to the concept of kind of thresholding uncertainties in the same way that you would quality levels, because it's certainly true that the uncertainties are saying something about the underlying data. So a good example of this actually is with sea surface temperature. So if you imagine a region where you've got lots of eddies or currents on the ocean surface, so you've got big changes in the temperature over a small area. I mentioned before that when we go to the level 3 data, we have a sampling uncertainty that is associated with the fact that we don't necessarily see the whole of the grid cell that we want to take an average temperature over. And I did some work to calculate how that sampling uncertainty should be expressed. And one of the things it's dependent on is the underlying variability in the surface temperature. That makes sense, right? The more variable the thing is that you're looking at, if you can't see all of it, then the chances are that the bit you can see doesn't fully represent the whole area. So where you've got ocean fronts or ocean currents, then you have a higher sampling uncertainty, which means that your total uncertainty is larger. So if somebody then comes along and they filter out the product based on high uncertainty values, essentially they get rid of lots of areas where we have ocean currents. And so they could be biasing their analysis without even really realising it, because the uncertainty is telling them something about the nature of that region.
So it's also really important to look at the uncertainties as well as the data itself.
So uncertainty is actually not completely a bug, it's more of a feature. It carries a lot of information. That's incredible, because usually errors or uncertainties in perhaps other scenarios have a negative connotation. They're unwanted. Then probably we should not call them uncertainties. We should call them something else.
What are the main challenges in terms of computing uncertainties? And I think in particular for satellite-based remote sensing, I guess there's so many sources of uncertainty that when you want to think about uncertainty propagation and trying to consider as much as possible, this is actually really challenging. Yeah, what's been your experience in trying to work with such complicated data and trying to calculate the uncertainty budgets?
So the first challenge is working out all the possible sources of error. One way it's a long process potentially, but it's quite prescribed. So you take the equation that is describing the measurement that you're doing and you literally pull it apart. You think about all of the terms and all the possible sources of error that come in. I think so often when we talk about how we construct these budgets, we talk about the terms themselves in the equation, and then we talk about these extra things which are not specified by the equation. And they're probably the most difficult one to get a handle on. So I've mentioned a couple of examples. So like the fact that we use a radiative transfer model, that's not explicit in the measurement equation itself. So that's something that we would have to think about in addition. And the cloud detection was another one of these things that is done as a pre-processing step. So it's not in the retrieval equation itself for land surface temperature, and therefore we have to think about that independently. So assuming that we can construct a full table of all of these error effects, and that's how we go about doing it, literally making a table of them all, the next step is to try and quantify them. Now, that is where it becomes particularly challenging. So you may have some information available, for example, the noise on the sensor, and that you can then propagate through. Some of the things you may be able to work out, a bit like the example we discussed with how deep you press the thermometer into the soil. There may be ways that you can to get a handle on what that is. So sometimes we know the actual values that we can propagate. Sometimes we use a model, which we would essentially be doing with that soil depth example. And sometimes there are times when it's just really difficult to know. So we know that there's a possible error, but we really struggle to know how we quantify the associated uncertainty. And the prime example of that is the cloud. Because if you miss a cloud and you essentially retrieve the temperature of the cloud, that observation has a really large uncertainty. But that is quite isolated because all of the ones around it might be perfectly good if your cloud screening is generally good. So how do you then specify that uncertainty within the product itself? Because if you say all of the observations have a 10-degree uncertainty associated with them, no one's going to use the data because it wouldn't give them the information that they needed to answer the scientific questions that they want to address. So that one is an example of where it's really tricky. So sometimes we have cases where we know that there's a potential source of uncertainty, but perhaps we can't quantify it fully or completely.
Previously, you've mentioned that also about educating potential users about uncertainties. Why is there a need to educate them? Do many users don't realize that this data comes with uncertainties? Or how do users usually perceive it?
It's quite a new concept, I think, to provide such detailed uncertainty information with these products. Historically, sometimes you just have one value for the whole globe, for example, or for one product, and suddenly users are confronted with lots of information that comes with every observation. So that's one change. I think it's also fair to say that historically, data would often come with quality levels. So they might have, levels 1 to 5, and 5 is really good data and 1 is really poor data. And these quality levels have a description of what they mean. And so users essentially would take the data and say, okay, I only want to use the good quality. I'm just going to take levels 4 and 5, for example. And then they would use all of those data just under the assumption that they were good data and that they meant what they said. So this is quite a new concept to think about. Each individual measurement has some degree of doubt associated with it. So it's this kind of change in thinking, I think, for users. And I think there's also this factor that it is quite mathematical when you get into the propagation of uncertainties. And not all users are in academia or have a particularly strong maths or physics background. There's loads of applications for these data. And I think that can be off-putting if it's not explained clearly and communicated what these uncertainties really mean.
So basically, the users were used to more blanket classifications of uncertainty, and now that there's so much of granularity, it's often difficult for them to perceive and work with them. Interesting.
And Claire, you're involved in a project by the European Space Agency, which is the LSTCCI project. So this is a climate change initiative putting a lot of work, I think, particularly into uncertainties in providing long-term stable land surface temperature data with associated uncertainties. So perhaps you could say a few words on the work that you've been doing in the context of this LSTCCI project and how you've been working with the users in trying to help them understand and adopt and uptake more the uncertainty information.
Yeah, so I think in terms of uncertainty, there's two aspects to the work that I do. So I'm very much involved in trying to characterise the uncertainty budget that we've talked about earlier in this podcast. So the kind of nitty gritty of working out what those error effects should be and the maths involved in that. So there is some real technical documentation out there on the details of that. And then on the other side, it's working with the users to communicate all of these findings in a way that they can be used well with the data in various applications. So I mentioned earlier that the climate research group, so that's a key kind of vehicle for this. So this gathers people that are specifically using data from this LSTCCI project, and they can ask questions of the data producers, and they can work with one another to support each other in using this uncertainty information in their applications. The other thing that we do is we run user workshops. So approximately every 18 months or so, we gather users together. And one element of that always is to communicate about uncertainties. So that might be me standing up and giving a presentation and trying to demonstrate how important they are. But also we've done kind of practical sessions where people have done some hands-on stuff with data and looked at how the uncertainties, or what the uncertainties look like, to start off with, what they can show them about the data, and then how to use them. So we do a variety of things. And I think finally we have some written examples as well of how to use uncertainty in different contexts. And I think probably as the project goes forward, we should provide some more of those for users too.
And I think also one really nice aspect of this LSTCCI project is that you combine lots of different sensors and lots of different data. And I guess uncertainty information starts to become quite important when you start combining different data sources. So perhaps you could also say a word on how you're dealing with it in LSTCCI, and also why it's important that people keep in mind when they're using different data sources that the uncertainty is actually really important.
Yeah, so you're right. The LSTCCI project produces lots of data sets. There's loads of satellites out there that make measurements in the right region of the spectrum that we can retrieve land surface temperature. So there are two ways that we might think about stitching data together. So the first is, if we're thinking in terms of climate, what we really need is a long-term data record. And with the exception, perhaps your listeners know about the MODIS sensors that have been in orbit for about 20 years, but generally sensors don't last that long. It tends to be somewhere in the 5 to 10 year window. So if you want to look at what's happening over 30 or 40 years, then you need to start stitching together instruments in a series. Now, the way that I've talked about uncertainty budgets in this podcast is that we start off with a particular sensor. So you're developing essentially an independent uncertainty budget, thinking about all of the error sources for each sensor. So if you look at a long-term record, you need to be aware that the uncertainties might be larger at the start of the record than they are towards the end of the record. Generally, it goes that way because sensors tend to improve in quality over time. So that's one kind of aspect that users may need to think about. It depends, of course, what question you're trying to answer with the data, but it's one thing to be aware of. The other thing that you can do with the data is try to, so imagine that you wanted to produce a global product of land surface temperature at a given time. Now, no one sensor sees the whole of the Earth at the same time, so you can't just do it from one sensor. So then you might want to bring in data from different sensors. So we have geostationary ones that they sit just above the equator, and so they see lots of the area of the tropics and around the equator, and they just see that area time after time. But then we also have sensors that are polar orbiters, so they circle the Earth 15 to 16 times a day, and they'll see mid-latitudes and higher latitudes. So you might want to combine the two. And so what we tend to do then is take two products, and for each grid cell, we pick the observation that is closest to the time of the data set that we're trying to create. So at the moment, we're not combining uncertainties from different sensors, we're picking the closest one in time.
And I guess this is quite important to still consider because we have lots of upcoming thermal remote sensing satellites from ESA, from NASA, from CNES and ISRO. And I think they'll provide options for users to have a really nice kind of long-term time series, but at high spatial resolution. So probably these satellite providers also need to consider providing uncertainties for the users for these upcoming missions as well.
Absolutely. And I think that is something that has entered into the minds of most data producers now. There's been a big drive with the European Space Agency Climate Change Initiative programme, and that covers not just surface temperature, but a whole range of other variables that are essential for understanding what is happening in our climate. And there's been a real drive in that project and in that community to be producing these per observation uncertainties, no matter what the variable. So I think this is the way of the future, and these will also be provided with the high resolution upcoming missions, or at least that's my hope.
Do payload engineers, or let's say the engineering team that's working on these thermal instruments, do they also quantify the uncertainties and communicate them in some way?
Yeah, so this goes back to the pre-flight testing. So when the instrument's set up and they do all of the testing of the sensor, that's the kind of data that we need to quantify the uncertainty budgets going through our retrieval schemes. So that is the most essential thing for satellite producers to share. Now, they don't always, but they're getting better. So they've been pressed quite a lot, I think, from people who are producing products to provide this information. It tends to be more available now than it was perhaps historically.
And if a user has never worked with uncertainty before, all of these concepts that we've spoken about are really confusing, or maybe something completely new. Where could they start in learning about uncertainty? Are there any great resources that you have in mind that you could recommend them to look at, or very simply start introducing some uncertainty analysis in their processing or in considering it in their processing chains?
Yeah, so in terms of what we provide in the LST CCI project, we have a product user guide, and that's probably the easiest place to start. So that's a document that's written for users that describes exactly what's in our products, and that describes what the uncertainty components are, and we'll cover some of the things that I've talked about in this podcast. There's also a more technical document that's focused on uncertainties, which is not really an entry level for users, but at the end there are a series of examples. So they went right to the bottom of that document, last couple of pages, it shows you how you use the uncertainties in processes that users commonly want to undertake, so coarsening data, that kind of thing, thinking about some of the examples that I've spoken about today. So that's two good places for users to start. Certainly in terms of a project team, we're always happy to talk to users about uncertainties. Our contact details are on the website, so we would say get in touch and have a conversation, and I'm more than happy to do that.
Great. Maybe you should put the 2 pages of examples at the top of the guide.
I think they will migrate to the product user guide in due course.
Sounds great.
Wow, this was so enlightening, because to me personally, as someone who's only worked with the upstream side of things, of building satellites, essentially the only uncertainty per se I was aware of was calibration errors. So I would group this was my umbrella term for all that you have described today. And I would just put it into the category of calibration errors. Yeah, the image team will deal with it. But wow, there's so much that goes on under the hood. And thank you so much, Claire, for explaining everything so in simple terms that I can understand, and also inspiring me to learn more, to triggering my curiosity. Now I'm going to check out these resources. And also I'm going to add the links to these resources in the description of the podcast episode to those who are listening. But thank you so much. That was a very enlightening episode.
You're very welcome. It's been great to be here.